Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and a very good morning. Alright, kita mulakan dengan bacaan umum kita Al-Fatihah. Okay, so today we will learn the continue of the HR diagram. Alright, so basically, if you look through what you have learned so far, this is actually the HR diagram, which is very important in terms of the stellar evolutions. Yeah. And of course, we do have several categories here, such as the main sequence, the red giant, supergiant, and also the white dwarf. All right, and it shows how does the stars evolve is, all right, and of course, it will take millions of years, a billion of years actually, and it's also based on the mass of the stars. Yeah, it based basically if the star is low massive, then there's a certain categories that might be evolved um, compared to the massive stars. Yeah, okay. So basically, we do have a main several categories here, such as the main sequence stars, which is the curve or the stars that at the curve trend or at the mid regions. Yeah, which is we can see the curve across the center of the HR diagram. And we do have also the red giants, yeah, which is more cooler, but somehow is much more luminous because of the size. And this is actually also to be thought as a dead star or a protostar. While for the supergiants category, we do have more luminous, yeah, but more cooler than the main trend stars. And the almost the final stage, we do have the white dwarf, and this is the very hottest stars, yeah, and less luminous. So the size will be much smaller compared to the supergiants and also the red giants one. And it's also thought to be the death stars, right? Which it will be radiates their energy. So this is where the masses of transfer of energy is much more loosest, yeah. So we can see how does the star getting small and smaller. All right. So don't forget about the protostars, yeah, which is the first stage of the stars. Is when we talk about the proto, this is the first stars, yeah, to be, and before that you do have the clouds. So we can have uh, uh, the big size of the clouds, yeah, before it move up to the protostars. Okay. In Hishar diagram, we do have the luminosity versus the temperature. So somehow there is also luminosity versus spectral class. Yeah, so we can have O, B, A, F, G, K, and M, which is represent the spectral class of the stars. Okay, all right. So we do have the most main trend where is we call as a dwarf stage. And in this case, the development of the large clouds of increasingly dense hydrogens, which is converted to the heliums, right, at a certain stage. And it will start with the gas and also a dust. And we do have the starting points where just start with the few hundred Kelvin. And this is what we call as a giant molecule clouds, yeah. Then it will move up to the nebula. So basically the nebula is actually the first stars also. And this nebula contain the gas and also a dust, yeah. And this is the beginning of the stars. So we can have the examples such as Orion Nebula, yeah, Crab Nebula, and many a lot of the nebula outside there. And in this case, the temperature will be increasing, but it's about the range of the 2000 to 3000 Kelvin. All right. So we have also studied about this one also, right? The mass luminous effective temperature, right? So basically, we need to see at each stage how does the mass of the star is for each category, and also not to forget the other parameters such as the luminosity and also the effective temperature. Okay. So we also have covered about this one, right? The relationship between the brightness and also the luminosity, right? So I hope that you understand this one, and you can see whereas it's very important for us, especially to determine the temperature of the stars. And instead of the size of the star, because we do have the radius. Okay. Alright, so we finished until this one, right? So until slide 33. Okay, so we can see the relationship between the luminosity and also the mass. And in this case, we can have the categories, right? So it based on the milliseconds mostly. And this is the final stage where it can also be related with the radius and also the uh, we can see the mutual as center of the mass, right? So basically, if we do have the example as such binary stars, so this is the two stars in the orbit about their mutual center. And we can have the relationship where the M1 divided by M2 is equals to R2 divided by R1, and this is proportional to A2 divided by A1. Okay, so what's more, yeah, instead of the other parameters, we can also detect the period of the any stars. Yeah, so this is based on Kepler's law, which is the third Kepler's law, and we can have the formula where the p squared is equals to 4 pi squared over g um, times with m1 plus m2, and then times with a power of 3. All right, whereas the a is actually the semi-major axis. Okay, so since the mass luminosity relationship can be have with the formula of L is proportional to m power of n, yeah, and it do have the range, whereas we can put n is equals to 2.3 if the m is less than 0.4 mass of the solar masses, and n is equals to 4 if the m is more than 0.4 solar masses. All right, so we do have the solar mass equals to 2 times 10 power of 30 kilograms. So this is very, very huge, very, very big. Yeah, the massive is very, very large. So we can use the sun as a comparison compared to put the value of the mass itself, yeah, of the stars. All right. So basically, this is the examples to show the relationship between the luminosity and also the mass compared to the parameter of the sun, right? So we can have L over L of the sun and also log M over M of the sun. So we put as a log formula here. And we can have at the center of this graph, it shows that the luminosity is proportional up to m power of 3.5 of the solar mass. So this is the range of the relationship between the luminosity and also the mass, solar masses. Okay. So from there, we can put, all right, and we can put the range for each stars compared to the solar masses for all categories of the parameters such as the luminosity, the effective temperature, yeah, the radius, and also the mean sequence lifespan. Yeah, so it shows the range, and we can also calculate easily, right, the range for each categories. Yeah, so we can see, for examples here, if the solar mass is about 0.1 solar masses, then the luminosity is about 3 times 10 power of negative 3, with the temperature 2900 Kelvin, and the radius is about 0.16 radius of the sun, and the lifespan is about 2 times 10 power of 12. So this is all shows up to 60 solar masses, and we can have, yeah, for example, even the solar mass of the sun can have one solar masses with luminosity, and it do have the effective temperature about 6,000 Kelvin. So it shows that our sun, for example, has the surface temperature is about 6,000 Kelvin. And of course, the lifespan is about 1 times 10 power of 10, yeah, years. So it still have a billion years here. And so we just imagine how about the other star is. So definitely, most of the stars is much more huge compared to the solar masses. And we do have the stars that up to even 100 or 300 solar masses. Yeah, up to now is 300 solar masses. Okay, so we move to the spectral class, which is very important also in the HRA diagram. And basically, we can put as a two categories here, which is a cool stars and also the hot stars. Yeah, and basically, if we have the cool stars, the range is about 1600 Kelvin to 2500 Kelvin with the color of red color. While for the hot stars, the surface temperature is about 35,000 Kelvin and above, right? And the colors is about, it looks like a bluish or bluish white, okay? So we can see the temperature and we can assume the range of temperature based on the color, okay? All right. Basically, we do have the range of the solar mass is about 0.1 to 100 solar mass, right, for each stars. And we can have the size from the white dwarf, for instance, with the which is about our size, our Earth size. And somehow this is also very supergiant stars here. And the size can be up to several hundred times compared to the sun, our sun. And this is the schematic diagram of the spectral class with the HD, which is represent for each stars. Somehow, that's if the star don't have any names, so you can put as a catalog name, such as HD 12993. So this is actually the one of the stars, yeah, the spectral class of one the star with the spectral class type is 06.5. Yeah. So since we have the spectral class which is represent O, B class, yeah, A class up to M class, and it shows either it is a hot star or a cool stars. And we do have also the others spectral class such as F4 metal poor, the M4.5 emissions, yeah, and also the B1 emissions. Okay. And this is shows here the intrinsic colors, the temperatures, and also the prominent absorption lines for each spectral class. So we can see the elements will be getting heavy and heavy once it's up to M class type. Yeah. And when we talk about the temperature, right, of course, the O class will be present the highest temperature compared to M class, and we do have about 41,000 Kelvin compared to 3,000 Kelvin for the M class. Okay, so in between of that is actually the range of the other spectral class. Okay, all right. So this is also the other schematic diagram of spectral class, but more specific because it shows the conventional colors, the apparent colors, right? And also the mass, and not to forget the radius, yeah, compared to the solar radius, with the luminosity, the hydrogen lines, and also the percentage, yeah, percentage of main sequence stars. So basically, this is much more parameters compared to before, all right? And we can see the range, yeah, for each spectral class with all the parameters. Okay, right. So if you look to the spectral class compared to the colors, so this is the schematic diagram where we can have the O class, which is bluish violet, blue for the B class, white cyan for the A class, white yellow for the F class, and then we do have a yellow like our sun for the G class, and we do have an orange for the K type, okay, and also M colors for red colors for the M class. Yeah, so this is the range of the colors with the spectral class. All right. Now we move to the other classes, parameters, which is what we call as the luminosity classes. And basically, it much more to shows the size of the stars. Yeah? We do have from the 0 up to 7. Or we can have hypergiants to represent the zero class. Alright, 1A is shows the luminous supergiants, 1B shows the less luminous supergiant, 2 represent the bright giants, the 3 is represent the giants, and then we do have the subgiants for the 4 class. 5 represent the dwarf. Yeah, so we do have the center is actually the Mesopus, and the Lumistic Class is actually in category 5. Alright, the 6 is represent the sub dwarf, alright, which is specifically on the population 2. Right, so you will learn what is the population 2 is in chapter 5. Okay, and we do have also the white dwarf for category 7. Okay. Alright, so where is the position of the Lumistic class? So we can see clearly, alright, from 1 class here. Actually, from 0 is much more higher compared to 1A, 1B. We do have 2 class, 3 luminosity classes, and then up to white dwarf. Right, so this is the luminosity classes that represent for the HR diagram compared to the HR diagram before, which is represent the temperature. Okay, so all of this one, this is all the examples that shows. Yeah, we have the Vega stars, which is the A hot white stars with the mass, yeah, compared to the Earth solar masses. So it's a lot of numbers here, and it do have the surface temperature about 9,000 degrees Celsius, right? And how to compare the type B? So this is the examples. This looks like a big hot blue star, the Regulus, and the surface temperature is about 20,000 degrees Celsius. Okay, and we do have the bright giant stars here with the surface temperature about 8,000 degrees Celsius, right? So it looks like more red stars, and it has also a lot of numbers compared to the Earth's masses here. Okay, this is called Canopus. Betelgeuse stars, yeah, one of the supergiant stars. You can see actually directly the stars here, and the surface temperature is about 3,500 degrees Celsius. All right, so this is actually the A Orion. Yeah, okay. And we do have also the Rigel. This is a blue supergiant stars, right? Also can be seen clearly in the night. And the surface temperature is up to 13,000 degrees Celsius. Okay. So how about the white dwarf, right? So we can see the white dwarf, but we need to use the telescope, right, to see the white dwarf, such as a Sirius B, right? So it is companion with the Sirius A. The Sirius A is not a white dwarf, but somehow the Sirius B is actually the white dwarf, and it do have the temperature is about 11,000 degrees Celsius. So it's still hot, right? But it's very small. Okay. Right. So we need to have a lens to magnify the CSP to see clearly. Yeah. How does the white dwarf is look like? So this is an example to show the CSP figure. Okay. All right. So all of these chapters, yeah, it is very important for you to understand and also to remember the HI diagram, because after this, we will go to details on the HR diagram, right? Especially in chapter 4 up to chapter 6. Yeah. So I hope that you can understand it. And this HR diagram also can represent a lot of schematic diagram, right? So you can see different schematic diagram that represent. Either it can show the luminosity, yeah, the temperature, the spectral class, and so on. So we can see and catalog all the stars inside the HI diagram. Yeah. Okay. All right. So this is another one also, right? To shows the HI diagram. Another examples. Okay. So what is the HI diagram is? It's actually represent as a Hertzsprung-Russell diagram, and it also known as a color magnitude. Yeah, color magnitude diagram, which shows the relationship between the absolute magnitude, the luminosity, classifications, effective temperature, right? And it's also be created by Ernest Hasbrons together with the Henry Norris Russell, and it's represented the huge leap forward in understanding the stellar evolutions. So this is very important, right? Because from the HR diagram, we can know the range from each categories, right? Such as the main sequence, okay, what is the mass of the stars in the main sequence, how about the range inside the supergiant categories and so on. So we need this kind of HR diagram, okay? And if we look, yeah, most of the star is occupied the region in the diagram along the line of the main sequence, yeah. And during this stage, the stars are fusing hydrogens inside their core, and it will also move up to the horizontal branch, yeah, whereas the helium fusions inside the cores and the hydrogen burning in the shell is, and others categories or others step of evolutions. And we do have the stars where we call it as a RR Lyra stars, which can be found in the left of the scape. And this is also the stars where we call as specific variables. So the magnitude will be different, all right, and inconsistently. This is reside in the upper section of the instability strip. Okay. Right. So it also used, yeah, by scientists to roughly measure how far the star cluster is from the Earth. So it's very important, right, to update the HR diagram. And it can be done by comparing the apparent magnitudes of the stars in the cluster. Okay, and basically we do have observed the group which is shifted in the vertical directions. Yeah. Okay. Right. So this difference in magnitude that was bridged in order to match of the two groups is called distance modulus. Okay, and we know as a main sequence fitting, or maybe we can call it as a spectroscopic parallels. Yeah. All right. And the HR diagram also can be used, right, to define the different types of the stars. Yeah? Basically, the theoretical needs this kind of HR diagram because they want to see the stellar evolutions, and they will make a modeling of the any categories of the maybe the galaxy and so on. So we want to see the HR diagram, and we need to refer the HR diagram before that, right? Okay, so that is all about chapter 3, right? I hope that students will ask the question in the next lecture, inshallah. All right, so with that, thank you very much. Assalamualaikum warahmatullahi taala wabarakatuh.